Hey guys, Mr. Palmer here with another set of physics review problems. I'm going to be looking at work power in simple machines. This is going to be part 1 where we're looking at questions 1 and 3 in your review, which have to do with work. You can pause, try them yourself, and then see how I work out the solutions. Let's start with number 1. We have a 60 kilogram cat. It says is pulled horizontally across a level floor with a force of 35 newtons for 8 meters. Find the work done by the applied force, the weight, and the normal force. So I think what you need to do here, like we've done in these many times before, is you want to draw in your forces. We're going to make our free body diagram. So it's telling us that there is a 35 Newton applied force, and I typically draw them to the right. Let me switch colors. It's going to be going a distance of 8 meters. So just draw the movement with a dashed arrow. And we have some other things. We know that it has a mass of 60 kilograms. So I'm going to draw in here 60 kilograms. Now that is the mass, not the weight. We're looking for the applied force, the weight, and the normal force. What are the work associated with each of those? So our equation for work is equal to force times distance. Right? And in this case, if we're using our simplified work problem, the work must be going, or the force must be traveling in the exact same distance, or in the same direction as our distance, as the motion. So in this case, let's start with A. A is going to be work equals force times distance. Well, we need to multiply the applied force, which it tells us is 35 newtons. And we want to multiply the distance, which is 8. That's going to give you 280 newtons. So that is our applied. In this case, we're not worrying about friction. We just want to take a look at the weight and the normal force. So let's complete our free body diagram. Of course, every object on Earth, we're going to have a downward force, which is going to be our force of gravity, the weight. And we have the normal force. If we're sliding it horizontally, right, it's pulled horizontally, so it's going across some surface. And in this case, if it's doing that, we know that the normal force and gravity are both equal. But when we go to calculate the work for each of these, let's take a look at part B. It says what's the work done by the weight. So that would be the force of gravity times the distance. Well, the distance in this case is a 0. We don't even need to calculate what our weight is. We don't have to take mass times 9.8 to find that out. We can simply say that this is 0 because we know that the distance is going to be 0. Likewise, for the normal force in part C, the work is going to have to be 0 because even though there is a force, we know the normal force is exerting a force, it's not moving in that direction, it's perpendicular. Okay, so let's look at number 3, which is the second one. I'm going to go on to that one. And this one has to do with also a work problem, which I'm doing these two together. So we're going to calculate work done by the applied force that pushes a 60 kilogram sled at a constant speed for 350 meters, and it's giving us a coefficient of friction of 0.27. So let me go back and draw our free body diagram again. This time we do have friction. I'm going to draw a dashed line to represent the distance that we're going to go. That's 350 meters is our distance. We know the mass, 60 kilograms, right? I'm going to write that in there. We're pulling it horizontally, so we've got a weight down. You know that's mg, and that's going to be equal to our normal force up, which is equal and opposite, right? Our weight, so Fn, we know that's equal and opposite to Fg when we go to calculate it. And it's giving us a coefficient of friction. It's telling us that mu is 0.27. All right, now the critical thing in this problem is that we know that it's being pushed at a constant speed. Okay, so back in the question up here, you see constant speed. Well, what is that going to tell us? Constant speed tells us that the net force acting on this is 0. That is, it's going to be balanced. that means that the applied force and the force of friction are going to be equal. So they haven't told us what the applied force is, but we can calculate the force of friction because we'll be able to get the normal force, and our force of friction is equal to mu Fn. Because, right, these two are equal, we said back here, we can also write this as mu Fg, which is equal to mu mg. So this we know. We have all of these values, so we're going to put in 0.27 for mu. We're going to put in the mass, which is 60. We're going to put in 9.8, and that's going to leave us with 159 newtons is going to be the force of friction. Well, let's go back over here. That means the force of friction is 159 newtons, and that means the applied force is 159 newtons. So now we can calculate the work. Work is going to be equal to F times D. We know that our applied force is 159. We're going to multiply that by 350, and that's going to give us 55,566. For some of these guys, you'll be able to work your way backwards. And again, joules, really important. The units of work is the same as the units of energy, and those are joules. I'll be back next with part 2.